So we are starting in on our discussion of the atom. Okay. Our atom, then we are going to be talking about like parts of the atom. And today is going to focus primarily on the history of how they figured out what the atom was. So if we go back in history to when thought kind of started regarding the atom itself, I'm trying to move this out of the way. There we go. It actually goes back to Greek philosophers. And when we're looking at this, we're talking about 5th century BC. So that would be like a long time ago. Okay. 5th century would be like 500 years before the birth of Christ. Okay. So that's a long time ago. These guys were talking about this. Back then, Democritus, he's the guy that came up with the idea of democracy. He argued that all matter was composed of finite particles called atomos. That was the Greek word for indivisible. So what he thought was that we couldn't, if we kept dividing stuff down and kept dividing it down and kept dividing it down, eventually we would get to a point where we couldn't divide it anymore. And that point he called atomos. And he thought that atoms then were different in shape and size, and they could be joined together. Aristotle then came along, and he said that we could make various things, and we essentially had 4 elements. Those four elements were earth, fire, air, and water. Which I think if you guys have ever been into Pokemon, that might have some sort of relevance to you, right? Didn't they have fire types and water types? Yeah. All right. He said that we could indefinitely divide back. So we could just keep dividing and dividing and dividing and dividing and never stop. That eventually, like, it's just going to keep going forever. And people followed his thought patterns for about 2,000 years. So now we move through history, and we are going to end up going here, and we're moving up to Dalton. Okay, so we've moved from 500 BCE up to 1807. Okay. And this is Dalton. This is a sketch of what he looked like. They didn't have photographs back then, but he was, somebody drew this. His atomic theory then came up with, I think it had 5 parts, if I'm not mistaken. Yeah. He said matter is composed of really small particles. He called those atoms. So he was kind of giving a nod back to the Greek philosophers that had talked about this. An atom is the smallest unit of an element that can participate in a chemical change. And we talked about that last chapter, where these chemical changes. An element then consists of only one type of atom, which has mass that is characteristic of the element and is the same for all atoms of that element. A macroscopic sample of the element contains incredibly large numbers of atoms, all of which have identical chemical properties. And we still accept that. I mean, that's still like accepted knowledge as far as this is concerned. Both of these postulates are still accepted. For example, if I had 12 grams of carbon, which isn't really that much, okay, if I had 12 grams, that's 6.02 times 10 to the 23rd atoms of carbon. That's a lot of atoms. Okay. He said that atoms of one element differ in properties from atoms of the other elements. Compounds then consist of atoms of 2 or more elements that, when combined together, are in a small whole number ratio. The numbers of those atoms of each element are always present in the same ratio. Again, this is still accepted. Number 4 is. Number 5, atoms are neither created nor destroyed during a chemical reaction. That's our conservation of mass law. We studied that last chapter too. Okay. They are instead rearranged, and we end up getting new substances formed when we go through chemical changes. All right. Any questions on this? Anybody still writing? Okay. So Dalton then came up with the law of definite proportions. And he knew of Joseph Proust, and that guy demonstrated that all samples of a pure compound contain the same elements and they're in the same proportion by mass. And that's what we looked at on your test. Okay. The ones that had the exact same percentages were the same items. The statement is known as the law of definite proportions or the law of constant composition. The suggestion that numbers of atoms of the elements in a given compound always exist in the same ratio is consistent with these observations. Again, we've talked about the law of multiple proportions. We talked about that last chapter. And that's how we're in a fixed ratio here. For example, water, there's always 2 hydrogen and 1 oxygen. Every time you have water, that's what you've got. If you change that ratio up, you don't have water anymore. All right, so here's our first problem. A sample of a compound is analyzed. It's found to have 4.27 grams of carbon and 5.69 grams of oxygen. Sample of compound B is analyzed. It has 5.19 carbon and 13.84 oxygen. They want to know, are these data an example of the law of definite proportions, the law of multiple proportions, or neither? And what does the data tell you? So first of all, we need to analyze that data and figure out what our proportions are. So we're going to start by doing the same thing we did last time, which was part over the whole. So for the first one, we would have 4.27 grams of carbon over. I need to add these 2 values together. 4.27 plus 5.69. So the total of these 2 together is 9.96. And then I'm going to multiply that by 100. And when I do that, I end up with 42.9% carbon. Now I'm going to do the same thing over here. 5.19 grams of carbon over, and I need to add these 2 values together. And that ends up being 19.03. So if I take my 5.9 and divide it by the 19.03, I end up with 27.3% carbon. Are these the same substances? No. The percent mass of carbon is different, so these are not the same substances. All right, we have another one here. We have a compound. This one has 14.13 grams of carbon, 2.96 grams of hydrogen. So I'm going to do part over the whole for this. So that's 14.13 divided by 2.96. So this is 17.09 times 100. That ends up being 82.7% carbon. So what I did was I took my part, I added the two values together. That gave me the whole. And then I divided them and multiplied by 100. The next one, we have 19.91 divided by 3.34. I'm going to combine those together. They end up being 23.25 times 100. And that ends up being 85.6%. Are these the same compound? No, these percents are not the same, so they're not the same compound. Okay, so these are neither. We don't have law of multiple proportions. Neither one is right, and we do not have the same substance here. Okay. All right. The next guy then was J.J. Thomson. So we're going from 1809. Now we're fast forwarding to the late 1800s. Okay. He used what's called a cathode ray tube. These cathode ray tubes used to be part of like TV sets back in the day before LED TVs. You may still have one like in your grandparents' like attic or something, or even in your basement. You may have one of these old tube TVs where, you know, they're massive beasts compared to like the super thin ones that we have nowadays. But when I was a kid, this is what a TV was essentially made out of. The tube then contained two metal electrodes. When the high voltage was applied across the electrodes, a visible beam called a cathode ray appeared between them. That beam then was deflected toward the positive charge and away from the negative. So remember, unlike charges attract. They were able then to calculate the charge to mass ratio for negative particles, which they ended up calling electrons. So he discovered electrons. This was his contribution. He discovered electrons. So kind of a big deal. This is what his apparatus looked like. And when they turned it on, this is the positive plate. These negative charged particles were attracted to that plate because remember, unlike charges attract. All right. J.J. Thomson. This is in 1904. So this is, I mean, and when we're talking about relative history of the world, this is not that far ago. Okay. There are people, I mean, there are people walking around right now that were born in the 1900s. Your parents, me, a lot of people, even one of my kids. Okay. He proposed what's called a plum pudding model of the atom. This is what a plum pudding looks like. It's kind of like apple bread, or sometimes you get like, you know, stuff like that. But in England, they eat plum pudding. It's a common thing. So that's where that term came from. He said that our atoms have these positives and negatives in them, and they're just kind of all in there together. Okay? So positively charged mass with an equal amount of negative charges just kind of embedded in there. Next guy comes around, and this is about the same time period. He proposed that the atoms were kind of like Saturn. Okay, we have a positive center, and then our electrons are kind of like the rings around Saturn. So that was his proposal, and he's getting actually closer to what we accept today as the model of the atom. Okay. Robert Millikan then, a few years later, came along, and he actually calculated the mass of a single electron. So extremely tiny here. Then Frederick Soddy, a couple years later, he came up with the fact that an atom could have types of atoms that with different masses that were chemically indistinguishable. And he called these different types isotopes. The atoms of the same element can have different masses. And we're going to talk about that later on. We're going to define what an isotope is in the next few days. So that is Frederick Soddy, and that was in 1913. So a little more than 100 years ago. All right. Almost 100 years ago, maybe a little more than 100 years ago. So in 1919, Ernest Rutherford then came up with the idea that most particles, when passed through foil, move straight through and aren't deflected. Because most of the particles pass through, that means that an atom is mostly empty space. So what he said was we have a small, relatively positively charged body in the center, which we call the nucleus. And he was the one that discovered and named the proton. So that's important to kind of realize here. Okay. He was the one that named the proton and figured out that those exist. And what he did was he had a situation here where he ended up having these atoms here, and he would shine these through, and most of them went in a straight line. So most of these dots, the purple dots, are going in a straight line. A few of them get deflected off, but most of them go straight through. And that's how he was able to figure out, oh, this is mostly empty space, because most of the stuff goes straight through. You get a few that are bouncing off, but most of them go straight. So that was his kind of legacy to science. And then we've got just a couple more guys here to cover tomorrow. Chadwick. And so we got about 3 or 4 slides that we got to get through tomorrow. And then you're going to have work time in class tomorrow for your 4-1.
So we don't have homework?
No, not tonight. I wanted to start 4-1 today, but I didn't get quite that far.
they will.